Hey, this is a video for 3.5, Population Growth and Resource Availability. So go ahead and check out the overview and set up your guided notes. So there's a few different population growth models that we have discussed, and there's a few other ones that I will introduce right now. For starters, whenever there is no limits to growth, we will see exponential growth. And as you recall, that is called the biotic potential. But sometimes the exponential growth will be limited, and in that situation you will see a die-off and a recovery. So this is fluctuating more so with the R-selected species, and the fluctuations would be less with the K-selected species. So sometimes competition or resource depletion will limit growth, and that is called logistic growth. And logistic growth is basically what we will see. This is an S-shaped curve, and this is the type of graph you would see with the K-selected species. And finally, the limiting resources that impact the population size, that is the carrying capacity. There is one other type of growth that you might have remembered from math class, but it doesn't really apply to populations, but it would be arithmetic growth. So for example, if two people move into a community every year, if it's a specific number that is added, that would be arithmetic growth. When we are doubling populations, that is exponential or logarithmic growth. So recall from a previous video that we talked about competitive exclusion, and this was the Gauss experiment. Basically what he did is he raised two different populations of paramecium, and he raised them together. And then what he did when he doubled the food amount for the paramecium, and you would think that both populations would double. However, that was not the case. One of them increased probably more than the other, but the other one wasn't really able to increase that much. And this is because no two organisms can occupy the same niche at the same time and be 100% successful. So this is along the lines of resource partitioning. This is why it occurs in nature. So I'm going to go through some population calculations. Whenever we're doing a percent change, it is always, and this you have to commit to memory, it's always final minus initial over initial times 100%. And you have to show this every single time. You even have to write this times 100, or you will not receive credit for free response questions. So the question reads, over the course of 1 year, a species population increased from 4,000 to 5,000 individuals. What was the percent change in the population? So I'm going to go ahead and annotate this. So we have final and initial, and the initial values are 4,000. The final values are 5,000. So what you would do is write 5,000 minus 4,000 divided by 4,000 times 100 is 25%. Now, one way of visualizing that, if you think 4,000 and 25% of that is 1,000. So we actually did add 25% of the original population got added to the final population. Okay, this one might have been a little bit easy. Let's look at a different one. Now this is a different type of population calculation. We're looking at, when we're seeing percent growth, we're looking at inputs minus the outputs divided by the total population. Again, this is an equation that you're just going to have to memorize. And when we're talking about population inputs, we really mean births plus immigrants. The population outputs, we mean deaths plus emigrants. So an immigrant is moving into the country and an emigrant is moving out of the country. And then I'm going to indicate the total population. So when I annotate this question, that will be seen in purple. So the question reads, one small town along the Jersey Shore has boosted their tourism industry. Last year, this 10,000 person town had an influx of 800 immigrants, while nobody left. Within the same time period, there were 300 births and 100 deaths. What was the growth rate last year? So, the original population, or the total population, as indicated in the purple, is 10,000 people. We had 800 immigrants. We also had nobody leaving. So that would be emigrants. So I just highlighted that because that would be the equivalent of 0. 300 births, that would be an input. And 100 deaths would be an output. So what was the growth rate? We have to first substitute. We have 300 plus 800 would be 1100. Minus, we have 100 plus 0, so minus 100, over the total population, which is 10,000. So we have basically 1,100 minus 100 over 10,000. That is 10%. And again, 1,100 minus 100 is 1,000 divided by 10,000. Really, you're moving the decimal over. It's an easy calculation. It is 10%. So when we talk about population growth, we really also want to think about how populations are distributed. So when populations are distributed randomly, there's really no rhyme or reason. And this might be from trees, because maybe the seeds were dispersed randomly, like a squirrel ate the seed or buried the seed randomly, or it was carried by the wind randomly. There might be uniform population distribution. This would be for organisms that are territorial. Like if you had wolves or coyotes that mark their territory, they may see a uniform population distribution. You also may see some clumped population distribution, and these might be animals that tend to herd, like water buffalo, like zebras, that may stay around water sources or something to that effect. Now, population density will affect their size. So if you look right here, this has a very high density, and this population, it is less likely to decline due to genetic diversity. In other words, there is a lot of genetic diversity present in a larger population, or at least that can be safely assumed. But when you have there are some things that can limit the population size. So these are called density-dependent factors. So a density-dependent limiting factor is something like available resources and habitat space. In other words, if you have a high population density, it's going to mean that the population density is going to limit, or it's going to be limited by the amount of resources. It will also be limited by the amount of habitat space. Another example of a density-dependent factor is disease. If there is a high density of the population, diseases can spread very rapidly between individuals. Now we see something that is not very densely populated, so they're going to have better protection from disease outbreak. And some density-independent factors, in other words, it's going to affect the population size regardless of the size of the population. And these are things like natural disasters. It doesn't matter if you have a population like this or a population like this. If there's a fire, it's going to kill everything. If there's a tsunami, most likely everything's going to die. If there's a hurricane, most likely everything is going to die. Likewise, when you have a low population, they're not going to be limited by resources when the population is not very dense. Also, habitat space will not be a limiting factor in this population because it is not very dense. So I gave you a lot of information. I would like you to respond to this check for understanding. And finally, with our FRQ practice, I want you to describe a density-dependent factor that affects population size. I hope that this video was informative. I thank you for your attention, and I will see you soon.